So today we are learning about voltage divider rule, right? And you might have come across these quite a lot, especially in numericals if you are studying the basic electrical. But today we will try to understand what goes behind the voltage divider rule and also see like the practical application so that it makes sense at least to you when you study voltage divider rule, right? So let's just start with what we learned previously. This, what you see here, is an example of a series circuit where two resistors are in series. First, you need to understand this. Voltage divider rule comes as an application of the DC series circuit, right? So, what was the output of the DC series circuit? Was that we learned to calculate the equivalent resistance of the DC series circuit. So, if I ask you, what's the equivalent resistance of this circuit, then you should be able to know now that Req equals to R1 plus R2. This is the output of the DC series circuit, right? So since you see end-to-end connection here and same current I is flowing through all of these resistors, if this is the case, then you can sum them up and say, or let's say you can replace them with a single R, which you call as Req. And the circuit becomes simpler now, right? So there is one R, there is one V, and there is one I. That means you can apply Ohm's law and you know what to do after that, right? So it becomes really easy. So the point is that, but see, there is a little twist in this because sometimes you need to calculate voltage across these two terminals rather than calculating current through the loop, something like that, right? And you might ask, okay, why do I need to calculate voltage across certain two terminals then? Is this a practical case application? Do we do that in real life? If you say that, here's the answer. You might need to do that because sometimes you might have a voltage source like this one used here. So you might have a voltage source, something like this. Okay, let's not use that. Let's use this. Okay, you might have a voltage source. Let's say it's your V and it's 12 volts. It's a battery, right? Makes sense. Now, you might have the two resistor system similar to what is here, right? Now, this is your R1, this is your R2, right? But the thing is, you need certain voltage level right over here. Let's say this across this R2, you want it to be, let's call this V2 as per the convention that you're using, right? Let's say we need to have this as 6 volts to make things easier, right? Now you understand, right? So this is our demand. This, we want it to be like this. We want it across R2 to be 6 volts because we want to use that somehow. Let's say that's our application, right? Now this is known. This is known because you bought it from the market, right? Now you need to design this circuit in such a way you get 6 volts. That means you need the values of these resistors is the second thing. So you need R1 and R2. Now, what is the value of R1 and R2? How many ohms, right? How much ohm? So it needs to be in such a way that it will fulfill this criteria which we are trying to design. That's it, right? Now, in this whole process, we have no idea how much current I is flowing through this circuit, right? And we have no idea what's R1 and what's R2. This is the whole point. And there's a formula that actually gives this V2 output directly, right? Without even calculating what's I running in the circuit. So that's the beauty of voltage divider rule. It makes things easier. That's why we are learning this. Now, coming back again, the same circuit again, right? So coming back. What we can do, let's say you want V1, right? What you can do is you can use Ohm's law. For using Ohm's law, obviously you need to know the current flowing through that element. So V1 can be written as I, which is flowing through the resistor, times the same resistor, right? This is true. Everyone knows that, right? Now, what we also know is if I is current flowing through the whole loop, then what I can write is the whole loop has this V potential now, right? Divided by Req, which is for the whole loop again. It's equivalent resistance where I replace all the resistors by a single resistor, right? And this is coming from Ohm's law again, right? V equals to IR, so I equals to V by Req, right? So we are replacing this with this term. It's understood. Cool. Now we know Req in this circuit, because this is a series circuit, we can write that as R1 plus R2. Simple, right? So we will replace that. And what we get after rearranging is something in terms of R and the circuit voltage V. Cool, right? Now we have a relation where we need to calculate R, or let's say place R values, and we know the V, and we can get V1, which is across R1, without knowing what the current is in the circuit. Though it came from Ohm's law, we are not using Ohm's law now, right? We'll use this as a formula. We'll learn this as a formula. It's not hard to learn. For example, if you want V2, you can directly go to the circuit and see, okay, if I need to calculate V2, I need few things here. First, this R2 divided by the series resistor equivalence, that is R1 plus R2, right, times the V of the whole circuit. So this would be the value of V2, right? Simple. Now let's make use of that and complete this design problem that we just discussed. So V1, we are not concerned about that. V2, this is our design problem. We need 6 volts across R2, right? Now let's continue. Okay, so you have everything. Now what you know is you can write V2. You would say, okay, I know V2. It's R2 divided by R1 plus R2, right? Times V. Now let's just substitute this. It's 6 volts, right? Equals to, now what you do not know is R1 plus R2. So this is like this, right? Let's put it on the other side. So it becomes 12 volts, right? R2 plus R1 plus R2 equals to, this is 0.5, right? You understood, right? We get this relationship now. What this means is there's no one right answer. You can use any combination of R1 and R2 such that it fulfills this relationship. Now, if this fulfills, like if any combination of R1 and R2, you can do hit and trial, let's say, that fulfills this relationship, and you get, let's say, 4 combinations, then every combination will give you 6 volts. So you can try to find that. Now the simplest answer here would be to use same values of resistor, because I'm just doing the speculation, because this 12 volts is getting reduced to half. So if you think about it a little bit, if you use same value of resistors, let's say 50, right, divided by 50 plus 50. Let's do that first, right? It would be 50 divided by 100, so it's 5 to 10, so it is giving you 0.5, right? So let's use 50 then. And this is how we got 6 volts here using 50 ohm resistors, right? But we can use other values of resistor as well. But the only constraint here in practical case would be how much current is flowing through the circuit, or let's say what's allowable there.